Good morning. Today we will continue the next chapter in electronic and instrumentation design, and we start to chapter 6 is about the DC and AC bridge. So we start with Wheatstone bridge. In this chapter we will talk about many types of DC and AC bridge that usually used to in the circuits and also to measure something. So we start with Wheatstone bridge. We can see from this figure that for the Wheatstone bridge circuit is content of 4 resistors here, R1, R2, R3 and R4, and R1 and R2 is ratio arms, and then there is a currents I1 and I2, and then we have the standard arm here is R3, and then this is the unknown resistor or R4 that contain the current is I4. So this circuit, the Wheatstone circuits, is used to determine the resistance is from approximately from 1 ohm to several ohm or mega ohm. So we connect the R1, R2 and R3 and R4 using this circuit to the source or E here. Okay, and then we have the galvanometer between the point C and point D here. Okay, the bridge is said to balance when the potential difference is 0. So we have the IC, like I said before, IC and ID is the ratio arm, and then we have the R4 this is unknown unknown resistor, and then connect to the standard arm or R3. So from this circuit we can do simply mathematics like this one. I1 R1 is equal to I2 R2 here. So we can see from this figure that I1 is equal to I3. So we can do this mathematics that I3 is E per R1 plus R3, and also I2 is equal to I4, that is E per R2 plus R4. Okay, then by combining this mathematics, then we can write that R1 plus R1 plus R3 is equal to R2 per R2 plus R4. Okay, then we can do multiplications. So R1 multiplied to R2 plus R4 is equal to R2 multiply R1 plus R3. Okay, so we can get that R1 R2 plus R1 R4 is equal to R2 R1 plus R2 R3. So because this is a similar, we have this is the similar with this one, so we can write that R1 R4 is equal to R2 R3. So we have the unknown element that is the R4. So the R4 is unknown element here. So we can write, or we can get that R4 is unknown element, or Rx is equal to R2 dot R3 per R1, or this is the ratio between R2 per R1 multiplied to the R3. So we can get that this one, the value of the R4 or the unknown circuits. Okay, so from this mathematics we can say that the unknown resistor or R4 is depends on the ratio between the R2 and R1, and also the standard element of R3. Okay, so we can, from this one we can know the unknown resistor by using this mathematics. Okay, so in Wheatstone bridge we can use the Wheatstone bridge or connect the unknown resistor here to some measurement things, and then from that one, using this mathematics, we can see, or we can know what is the value of unknown resistor or R4. Okay, but if we use the Wheatstone bridge, we have many limitations. Is, for example, if the value of unknown resistor or R4, if the value of the R4 is very small, so the connections, I mean that this is the connections and then this is the connections, so it will be affects the measurements. So from this one, from Wheatstone bridge, we cannot use the Wheatstone bridge to measure the very small unknown resistor. Okay. Then another limitation of Wheatstone bridge is the thermal electromotive force in the bridge can affect the balancing of the bridge. Okay, so if we connect resistor, sometimes we can get the thermal energy. So the thermal energy in the circuit will affect the balancing of the bridge. So if the balancing of the bridge is affected by the thermal electromotive force, so the Wheatstone bridge is not ideal. So we cannot use the Wheatstone bridge to measure the unknown resistor. Okay, and then another limitation is the change in the value resistance in the arm of the bridge can, sometimes it will be happens because of the rise of the temperature. I mean that if we connect this Wheatstone bridge to the source, sometime the thermal, sometime because of the current is little bit high, so the thermal on the temperature in the R1 and R2 is increased, so it will be affect the measurement of Wheatstone bridge. So this is some limitations of the Wheatstone bridge. You can see this limitation in the textbook. And then okay, we can use the mathematical model of the Wheatstone bridge using the Thevenin's equivalence circuit, as you can see in the figure 6.2. We can see here, this is the Wheatstone bridge configurations, and then if we want to make, or we want to draw another type of this Wheatstone bridge, we can use the Thevenin circuits. So this is we look the circuit using the C and D here. So this is the C and D. So the C to A is connected to R1, so this is the R1s, and then A to D is connected by the R2, and then C to B is connected to the R3, and then B to D is connected to the R4. And then for the A to B, we connect or we make the assumption that the A to B is connected by the RB here. Okay, so look for the C here. This is the total or the final simplification model using the Thevenin equivalent model. We can see here that the IA here, this is the IA or IG, is equivalent to the A Thevenin per R Thevenin plus RG. And then if we use the Thevenin open circuits, that is the CD here, this is the C and D, so the ECD or the potential difference between the CD is equal to EAC minus EAD. Or we can see here, this is the C and D. If we want to measure the potential difference between the CD, we can use this one, the EAC minus EAD. Then we can see that EAC or here is I1 R1s minus I2 R2. Okay, where we can see here that I1s is equal to E per R1 plus R3, and I2 is E per R2 plus R4. Yeah, we already like this one. Yeah, we already draw the mathematics in the previous slide. So from this one, we can get that ECD is equal to E multiplied by R1 plus R3 minus R2 per R2 plus R4. Yeah. Okay. So this is so we can see or we can measure the potential difference between the CD using this equivalent model. Okay, so if we want to know the simplification Thevenin equivalent circuits, so we can look at the figure B here. So we can see that R Thevenins is equal to R1 R3 plus R1 plus R3. So it's like the parallel connections between the R1 and R3, and it is equivalent to the R2 R4 plus R2 plus R4. Okay, because this is the parallel and this is the parallel, so we can see the R Thevenin is the parallel connection between the R1 and R3 and also the R2 and R4. Okay, so if the null detector is connected to the point C to D here, this is null detector. So we can measure the current between the C to D, or IG, is equal to A Thevenin per R Thevenin plus RG. Okay, where the RG is the internal resistance of the galvanometer, and then the R Thevenin is this one. Okay. Okay, so this is the Thevenin equivalent model for the Wheatstone bridge. Then after we talking about the Thevenin equivalent model, we will talk about the Kelvin bridge here. So please look at the figure 6.4. This is the Wheatstone bridge circuit showing that the resistance R of the lead from the point M to the point N. So we have the resistor here, small resistor R here. Okay. Then Kelvin bridge is use the principle of the Wheatstone bridge, but if we want to measure the very small unknown resistor from the 1 ohm to the 0.00001 ohm, so we cannot use the Wheatstone bridge because the Wheatstone bridge has many limitations, like I said before. So if we have the R, very small r here from point M to N, so we have to use the mathematical equations that the R and P plus R and P, so the resistance between the N to P per resistance between the M to P is equal to R1 plus R2. So we have the balance equations that the Rx plus R and P is equal to R1 plus R2 multiplied by the R3 plus RMP. So from this one, we can see that if we make a substitution between these two equations, we can see that the Rx plus the R1 plus the R1 plus R2 multiplied by the Ry is equal to the R1 plus R2 multiplied by R3 plus R1 plus R1 plus R2 multiplied by the Ry. So we can get the simplification of this one is Rx is equal to the R1 plus R2 multiplied by R3, like on the Wheatstone bridge here. Okay. So in these situations, if we use the Wheatstone bridge to measure the very small resistor here, or we have the very small resistance here, so we have to eliminate, or we cannot see the effect of the small resistance here because of, we can see here many variable we don't care, so we got the equation of the Wheatstone bridge. So to overcome these situations, so we use the basic Kelvin double bridge circuits you can see in the figure 6.5. So in the 6.5, we connect or we add more resistance here between the P to M and also the P to N is the resistor A and B, and also we connect the M and N using the Ry, like the Wheatstone bridge before. So in this double Kelvin double bridge circuit, the ratio between the R1 per R2 must be equal to the RA per RB. So by using the balance bridge, we can see that the E of the KL is equal to E of the LMP. Thus the KL is this one, the key to L here is equal to LMP, so it's equal to this one. So this is the balance bridge. So the EQL is equal to the R2 per R1 plus R2E. So it's equal to the R2 per R1 plus R2 dot I multiplied by R3 plus Rx plus Ra plus Rb Ry per Ra plus Rb plus Ry. Okay, so we got that the ELMP is equal to I dot the R3 plus Ra per Ra plus Rb multiplied by Ra plus Rb Ry per Ra plus Rb plus Ry. Okay, so after that we have the equivalent circuits. So this one I draw here. This is the equivalent circuits of the Basic-Kelvin bridge. Okay, this one is R3 and this is the RB, this is the RA and this is the P point, this is the M and this is the RY, this is the N and this is the Rx. Okay, so by equating the EQL and LMP for this situations, for this mathematics, we can solve for Rx, and then for zero deflections the EQL is equal to the ELMP. So this is the zero deflections. Okay, so yeah, we EQL is this one, this and this these equations is similar with these equations. Okay, so we can get that the total, if we use this EQL is equal to this ELMP, we can get that the final is Rx is equal to the R1 R3 per R2 plus Rb Ry per Ra plus Rb plus Ry multiplied by R1 plus R2 minus Ra per Rb here. And then by choosing the R1 per R2, this one, by choosing that this R1 and R2 is equal to the Ra Rb, so we can eliminate this the second term of these equations. So we can write that the Rx is equal to R1 R3 per R2. Okay, so the Kelvin bridge in these situations we can use to measure the very small, the unknown resistor here, Rx, because in this situation we consider the resistance between the M, P and N. Okay, so the after we learn about the Kelvin bridge, the Kelvin bridge and also with Wheatstone bridge circuit, we use this phenomena to develop the strain gauge bridge circuit like this one. So it is very similar to the Wheatstone bridge here. Okay. So we have the 4 resistor R1, R2, R3, and also Rx. And Rx is strain gauge under test, so we can use, or if we want to measure some parameters like a force, pressure, stress, we can use these circuits. I mean that the parameter that we want to measure is connected to the Rx, or we can replace the Rx using the parameter that we want to measure. And then we have the standard strain gauge. This is the R3 and also the R1 and R2. Okay. We can see from the situation that if the balance is I1 is equal to E per R1 plus R3, and also I2 is equal to E per R2 plus R3. Okay, so because of the Rx is connected to the parameter, so the Rx will be changed if we have the delta Rx. So it is like this is the changing of the parameter. So the new value of the Rx here is the Rx plus delta Rx. Okay. So if we have the imbalance circuits or EO, so if we have the imbalance circuit EO, so EO is equal to I1 R3 minus I2 multiplied by Rx plus delta Rx. Okay. So we got that EO is equal to E. So we replace I1 by using E per R1 plus R3 dot R3 minus I2 is E per R2 plus Rx plus delta Rx multiplied by the Rx plus delta Rx. Okay, if the arm bridge is equal, so the R1 is equal to the R2 is equal to the R3 is equal to Rx, and this is equal to the R. So if this is the equal arm bridge. So we can use the EO is R per 2R minus E per 2R plus delta R multiplied by the R plus delta R. So because of the R1 is equal to R2 equal to the R3 is equal to Rx, so we can get this mathematical situation here by these mathematical equations. Okay, so we can get that E0 is R plus 2R, so we can cancel it, minus E per 2R multiplied by 1 plus delta R plus 2R dot R minus 1 per delta R per R. So we can replace this one. So we got that E0 is E per 2 minus E per 2 multiplied by 1 plus delta R plus 2R multiplied by 1 plus delta R plus R per R. Okay, then by using the mathematical situation, and you can see for sure for the complete equations in the textbook, we can get that the final is E0 is equal to E delta R per 4R. So this is the approximate equations for the imbalance output voltage. So from this one we can see here, if we have the delta Rx here, if the parameters is changed for the specific value or this one, so the E0 will be changed. Okay, so the E0 will be changed here. This is the E0 here, imbalance output will be changed. If the E is constant and R here is constant, so this one is changed, so E0 will be changed. This is like linear, so the changing of the delta R will be changed the E0. So we can measure the parameter using the strain gauge bridge circuit because of these mathematical equations. So I think this is all of the learning video for the chapter 6, and then you have we have the another model of the bridge, so you can you can learn from the textbook. That is the AC bridge, Maxwell bridge, high bridge, Skering bridge, Wien bridge, Anderson bridge, resonance bridge, and also RF bridge. So I think this is all my presentations. Thank you for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.